All right, so the addition rule it's simple in that the mathematical operation that you're going to perform is just addition. All right, so you're just adding two probabilities, or subtracting, because subtracting is a special form of addition. It's just a question of, all right, well, how do I know it's going to be an addition rule situation? Right? If you see the word or in a probability question, you're adding. It's as simple as that. All right. But again, simple in the world of probability just does it means just not complex. It doesn't simple and easy doesn't mean easy. Simple does not mean easy. That was weird. So I see the word or. It tells me I'm going to have to add in some capacity. Now the question is, okay, now what am I adding? All right, so that's another thing. Card is being selected from a standard 52 card deck. Determine the probability of either a 7 or an ace being selected. All right, so you can go back to the sample space. I think it's 2 or 3 pages prior. The whole display of the entire deck of cards, and just start counting. But I can tell you that there are 4 sevens. You have the 7 of spades. I'm going to attempt to draw a spade. Well, it's not a bad spade. 7 of clubs. 7 of hearts. And 7 of diamonds. All right. And I have all the same stuff again, just for aces. Which means I got to draw those things again. Damn it. Yeah, there goes my spade. Club is terrible now. Heart never looked good to begin with. Oh, now I'm just copying the thing and yeah, I was so concerned about the shape that I lost the number. Thank you. And the reality is, for a question like this, you probably could have answered it 7 or 8 times before I drew the pictures. So, like that gives you a sense of just how straightforward some questions can be. All right, because if any of these cards come up, all right, now cards can't raise their hands, but like if you personify them, they could, like imagine those cards are like little people. All right, so you got your deck of cards standing around the room. All right, if you're all visualizing whatever the sample space is during a test, if you're visualizing the sample space just milling around the room, and that every time you're saying, okay, I need you folks. Raise your hand if you have these characteristics, and you could actually see the aces raising their hands in their little costumes. Then you got the right idea. All right. Then you're doing it the way I think you're probably best served to do it. All right. So you got all the cards. They're all like regimented because like I kind of imagine like they're the king's court. So there's very like regal and militaristic and all that stuff and fine clothing and things like that. So they're all standing here. They're all set up like a chessboard. And then I say, all right, raise your hand if you're a 7 or an ace. And then 8 hands go up because all the 7's hands are going to go up and all the ace hands are going to go up. And okay, you're 7 or ace. Which one are you?
No, I'm just curious. So does that mean that we have 4 of each?
Yes. Yep. And that's going to get me to my next point because you could look at your sample space and say I have 8 out of 52. And I know there's 52 because it's a 52 card deck. Now I could also say if I know individually the probability of getting a 7. Let me not close the parenthesis yet. Hold on. I'll use the notation. Well, similar notation. Probability of 7 or an ace. would be the probability of getting a 7 plus the probability of getting an ace. Each one of them is going to be 4 over 52. Add them together, and you could get your 8 out of 52 that way. But if you really think about it, aren't you really doing the same thing? You're doing the same thing, just adding the two numbers together instead of counting them all up. All right? One just has a little bit more notation. Now, I'll just do a simple Venn diagram here, nothing too crazy. I just want to illustrate something. I'm not going to ask you to make Venn diagrams. On a test or anything, but here's my 7s and here's my aces. I just want to illustrate that there's no overlap in the sets. All right, there's no way you could have a 7 or an ace, a 7 be an ace at the same time. Sevens and aces, they exist independently of one another. All right, so a card cannot have, the way a deck is structured, a card cannot have both a 7 and an ace on it at the same time. All right, so there's no concern for that kind of overlap, which we're going to deal with in the second example. That's why I bring it up. But this is known as being mutually exclusive. Mutually exclusive. All right. Now, it's kind of an interesting word or term. There's another word for it, disjoint. I don't like it. That's the only reason I don't use it. I just don't like the way it sounds, the way it feels. I like mutually exclusive. Honestly, I think I'm just kind of a creature of habit. When I first learned statistics, I learned mutually exclusive. The first stat class I took, then the second stat class I took, I had a teacher that used disjoint, and I was not the best student, so I zoned out a lot. I also thought that I was smarter than I was, or maybe I was just as smart as I thought. I had it figured out perfectly, but couple that with not paying attention. So I say that because maybe they explained in class what disjoint was, but maybe they didn't. If they did, I missed it. All right. So most of the semester goes by, and I'm like, what the hell is disjoint? There's no Google, by the way, at this point. So I'm getting more and more frustrated by this, and I'm not one of the people that goes and asks for help. So that's a failing on my part. But I'm like, this is really bothering me. I don't know what disjoint is, and I'm trying to pick it up from the context of the problem. And like 3/4 of the way through the semester, the professor is using the term disjoint in context, and I'm like, do you mean, in my mind, I never said this out loud, do you mean mutually exclusive? Damn it, has he been talking about mutually exclusive this whole time? The whole time? And so, like, I reflected back on the whole course. I feel like I could have been understanding this every step of the way, just based off of a word or a term that I knew. That sucks. So part of it was pigheadedness, and another part of it was just I didn't like the term. And then I developed a resentment for it because of a negative experience. So I use mutually exclusive, but the reason why I tell you this story is because it's not much of a story, but the reason why I tell you this is because the OpenStax textbook. You might go in there and you might see disjoint, and you'd be like, what the hell is that? You haven't gone over that in class. When you see it, you're going to think back to this moment because I contextualized it for you, hopefully. It's always the goal anyway.
So it's okay, is it mutually exclusive or disjointed?
Or disjointed, yeah. Some people actually like disjointed because it makes it kind of ties together with the idea of two things being separated, right? I like mutually exclusive because I think of two people that just kind of like broke up, boyfriend and girlfriend. They're no longer together. Like they're not exclusive. They used to be like uh, together, inclusive, and now they're excluding one another. I don't want you near me, and I don't want you near me either. So you got it. It's going both ways. I guess you could also sort of expand that to other things, but then you start getting a little too creative. So a card is selected from a standard 52 card deck. This is a copy paste job. You can see that, all right? And that's my preamble for pretty much every card question, just to give you reassurance that it's not going to be a trick question. It's a standard 52 card deck, right? Because what's the natural inclination? Oh, are there jokers in here? Like what kind of deck are we talking about? Is he going to try to mess with us? Is it going to be half of the deck? Is it going to, if this statement isn't there, then I have to give you the deck. All right. So if I'm going to say a card is selected from a fictitious deck where all the jokers have turned into alien, whatever, I have to give you the diagram that represents that sample space. All right. So it's kind of like a little bit of reassurance. Determine the probability of either 7 or a red card being selected. Now, I'm not going to draw a diagram for this. I'll tell you that. I mean, I'll do the Venn diagram, but I'm not going to label out all the possibilities because there's a lot of red cards in the deck. I don't want to do that. But what I will do is write probability of getting 7 or red. Now, I could look at that and say the probability of getting 7 plus the probability of getting red. All right, but we're going to run into a little bit of an issue here because some of the reds are already 7s. All right, so let's say I do that. I do 4 out of 52. If you go back to the sample space, you see that there are 26 cards in the deck that are red in general. And then I'm going to make a little note here. But 2 of the reds are also 7s. But 2 of the reds are also 7s. Which means that we're accidentally double counting them. So what I want to do is I want to subtract off those 2 reds, those 2 red 7s, 2 out of 52. All right, so what I want to do is kind of add a little extra ingredient to my formula, subtracting off the overlap. That's if you go back to the diagram of the deck of cards. Yeah, if you just count up all the red cards, there's a total of 26 of them. Just go back. So this one. So all of these cards. Oh, well, yeah, but the issue with black and white photocopies.
So I mean total of red cards are 26 and total of black cards are 26, which makes 52.
Correct. So in your mind, change it from black and red to black and gray. So, or shade it all red with crayons. Anyway, so minus, so I'm going to change my rule a little bit. Minus the probability of cards being 7 and red at the same time. So 7 and red. Now, you could kind of streamline that and say red 7s. You know, any way that makes sense to you, but the idea is that you'd have to account for the fact that they can be both. All right. So we subtract off the overlap so that we don't accidentally double count, because physically what this would amount to is the sevens the seven of hearts and the seven of diamonds raising their hands twice. And that, I'm like, well, I already got you. Why would I want you to, why would I count you a second time? Right? So
So yes, on the test we should write minus P7, that's part.
well, you got to write the minus 2 over 52. Whether you write the notation form is up to you. Yeah, because the notation here is really just to help us understand the concept. On the test, if you demonstrate the concept, I'm fine. So just the numbers.
I have a question.
Mm.
So, 4 or 7, and then it's 26 or red.
Right.
So, 2 minus 2 or 7 is red? I don't get it.
So
Please, thank you.
if you go back to the sample space here, what we're doing is we're counting up all of the 7 cards, which are 4 of them. And then if I count up all my red cards, there's a total of 26 of them. That's going to give me a total of 30 if I add those two numbers, right? 26 and 4. Right? But if I were to count up the cards that are either red or 7, and just physically count them up. 1, 2, 3, 4, 5, 6, 7.
So you remove it to black 7.
11, 12,
No, the red one.
13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. There's only 28 cards that satisfy the situation. But if I add 26 and 4, I'm going to get 30. So what that means is if I were to actually count up all the red cards, if you physically count up all the red cards, you get 26 of them. But in that process, I'm counting the 2 red 7s. If I count all 4 of the 7s, I'm counting those 2 red 7s a second time.
Oh, okay.
I can't count them a second time. So that's why we subtract them off.
Thank you.
All right, no problem. The issue is, because what happens, people look at this and say, okay, well, I'll just count. I'll just go through and I'll count the cards. And I'd say, okay, well, what if it's not that? What if it's something like a much more elaborate sample space? Like you have something with, let's say, 2,000 entries in it. I mean, here, when we're talking about dice, you roll a die 3 times, you're already up to 216 outcomes. If you're trying to physically count the number of outcomes that fall into a category, you're going to run into a problem, right, time-wise. So you want to make sure that you're looking at this formula and using it.
I'm just trying to get back to her question. So basically the 28 is the number for the red cards by counting twice the 7s, or?
The 30 is the number of cards overall if you accidentally counted the red cards twice, the red 7s twice.
Okay.
28 is what you get when you remove that double count. The extra 2 7s that you accidentally counted twice, if you remove those out, that's what you would be left with, and that's the correct value.
Okay, so that's what we have to counting twice minus 2 that will give us.
Right, the ones that are overlapping, yeah. So it's it's kind of like the idea of going back to the left-handed, right-handed example. If I were to say, okay, raise your hand, like I need males that are right-handed and females that are left-handed, and I start asking people all these different questions. Eventually, you're going to have people that are going to raise their hand for multiple things. All right, but if you only want the unique person, I don't care how many times they raise their hand. They can raise their hand 7 times. I just want that one person to be in my group. All right, so that's what's happening here. The red 7s, the hearts and the diamonds, they raise their hands for being 7s, and they raise their hands for being red, but they're still the same card. So it doesn't matter. They could raise their hand 30 times. It's still one card. right? So you have to account for the fact that they're only one card, but they have multiple categories that they fall into. All right. So it's very strange, and I would say that this one concept, this one problem, is what makes probability challenging. All right. When people say probability is hard, they're talking about this concept here, because once you get past this, just about everything else is based on procedure and perseverance. All right. In the form of a Venn diagram, what this means, I think it's kind of obvious by now, but you would have a set of red cards, and you'd have a set of sevens, and then you'd have some overlap between the two. So I'll just kind of shade it in here. That set is the red sevens. All right. Now we're looking at something here that it really doesn't have a name, or at least not a meaningful name. Like the last one we called mutually exclusive. This one is not mutually inclusive. You know, you don't just change the connotation. It's just not mutually exclusive. All right? Because inclusive would imply that one could be absorbed, well, one would be inside the other. That's not necessarily always going to be the case. Maybe it's just an ever so slight overlap. And in fact, if I were to take all possible numbers, so go from 2 all the way up to ace, you'd see that each one, I could create a circle going around red, where each one of them is basically orbiting red, having a little bit of overlap with the red, kind of biting into the red, because each one of them would have 2 of their sample space that is corresponding with the red set. Right? So, but you know, like these are the quote unquote simple probabilities. They're supposed to help us understand the like when we want to try to apply probabilities to the real world. So we're only using this as a means to an end, because you know, like you're not going into, well, not everybody, I guess. You're not going into whatever field is associated with decks of cards. You know, like you're not going to specialize in decks of cards. You know, you're gonna use some concepts of probability in real life, but we're going to take this concept and try to merge it with some other things that we're going to learn that's real life in nature. So that brings us to the general addition rule, but we just really kind of discovered that. So hopefully that's not a formula that you need to memorize, because it's really just the idea of overlap. If you have something in common between 2 sets, then there would be some kind of overlap. All right, this represents the overlap between 2 sets. So overlap between 2 sets. All right. And so the addition rule for mutually exclusive events, I would say you're probably not going to be as interested in that, because it's as simple as saying, well, if there's no overlap, there's no need for this part of it. So this general rule just collapses down to the first 2 probabilities being added together. All right, so the problems that follow, they're just kind of rehashing what we just did. So I'm going to put some stars on these bad boys and tell you to take a look at those on your own. We'll start class off next time with these questions, and that'll kind of guide us moving forward. But now we're going to move on to multiplication and conditional probabilities, which I would not I would not get too alarmed over, because We're not gonna go too far into it. But it's always a graph, so we're gonna do that. But it's gonna be a graph by hand rather than on a calculator. So the multiplication rule is talking about the situations in which you have more than one trial. So instead of just taking one card out of a deck, you might be taking 2, 3, 10, 100 cards out of a deck. So in this case, 2 or more trials are being conducted. So multiplication rule, multiple events. More than one event, you're going to be multiplying in some capacity. Generally, it represents any situation in which you see the word and. So multiple events involving the word and. All right, but the key is that it has to be multiple events. My first go around in probability, that got me. Because in the last topic, the or situation, we used the word and. The overlap, that was and. But we didn't multiply there. So I was like, wait a minute. If I'm supposed to multiply when I see the word and, why didn't we multiply there? That had and in it. This is confusing. And then somehow it got lost on me that it had to be multiple events. All right, so in those cases, I'm only taking one card out of a deck. Single card out of a deck. All right, one thing is happening. Here I'm going to take 2 cards out of a deck. Or I'm going to roll a die and pull a card from a deck. Or I'm going to roll a die, flip a coin, and pull a card from a deck. All right? Or I'm going to roll a die, pick a card from a deck, flip a coin, and then take a jog around the building. These are all events that could happen, right? But it's not just going to be the one thing. It's got to be multiple things. So the example here is a coin is tossed and then a die is rolled. Construct a tree diagram for a flip of a coin and a roll of a die, and find the probability that you toss a heads and roll a 5. So let's not worry about that part just yet. Let's toss the coin. So here's our coin. 2 outcomes when you flip a coin. Fair coin. Heads or tails. All right. Once you place your outcomes, draw little branches going to that, because you got to start somewhere. That somewhere is really me. I'm the one doing it. All right, so this is the experimenter. You could say me. Yeah, you play a role in this because somebody's doing the job. Tony is flipping a coin and then rolling a die. So the start would be Tony, right? Because that does play a role in all of this, right? Because you might not think that how a person flips a coin or rolls a die or spins a wheel might have an impact on the probabilities. But if that's the case, then you've never been to a roulette wheel at a casino and seen the dealer when they spin that ball around the wheel and it lands on 8. And you're like, okay, cool, I had 8. Better not bet that again, because what are the chances that that's going to come up a second time? Then it comes up immediately again, and again, and then again. And I'm like, how is that happening? And then the person nudges you and says, this dealer does it all the time. They can hit their spot. They're so skilled with the ball and the timing of it that they know just when to release it in order to hit the same spot that they got on the last turn. And it's like, wow, that's crazy. I mean, to have that kind of dexterity and also experience, that at a minimum, it's cool, but then also you throw in how it impacts the probabilities. It's like, well, do I want to use a dealer like that or somebody who is completely random? Well, random, I guess, if I don't know any better. But if I know going in that that person's going to hit their spots, then it's like, okay, it came up as 2. Maybe it's going to come up as 2 again. I'm not going to bet the farm on it, but maybe I'll put $100 down and see what happens. Paying out at 35-1, you know, so that could be a good move. But the me part of it is important. Right? In this case, it's just a dice, a coin and a die. So you could assume it's a random generator, some computer technology, something like that. But in the absence of any information like that, it's just you. You know, you're the one doing it. You're the one flipping the coin. All right. So after you flip the coin, you roll the die. And again, everything looks terrible when taken out of context. Die, again, is just a singular of dice. All right? That's this thing. It's not a command. There are 6 sides of a die. All equally likely to occur. So 1, 2, 3, 4, 5, and 6. So if I flip a coin and then roll a die, the possibilities are that I could flip the coin and get a heads, then roll a die and I can get any of these outcomes. I can get a heads and a 1, heads and a 2, heads and a 3, heads and a 4, and so on. All right. I can do the same thing assuming that the first outcome was tails. I can get any of the 6 possible outcomes for a die after that. See if I could do a copy paste job here. Oh, it's group. Okay, clone it. Well, something. Well, I'm just going to get rid of this because it's not going to fit. And I'm short a black line, I think. Just going to start drawing. Yeah, I only got 5 there. Took me longer to try to figure out how to copy paste it than it did to actually write it. My T looks a little short, so I'm just going to make it a little bigger. Ah, it looks great. Now my H looks short. Oh, it looks wonderful. There we go. Problem solved. Now, in order to be a correct tree diagram, technically, you're supposed to indicate all the probabilities on each one of the branches. Saturday morning. Don't want to do that. It's a uniform distribution, which means that the probability of getting heads and the probability of getting tails are exactly the same. The probability of getting a 1, 2, 3, 4, 5, 4, 6, exactly the same. There's 6 sides to a die. Each has the same amount of surface area. So the chances, and it's balanced perfectly. It's a fair die. So the chances of you landing on a 1 is the same as the chances of you landing on a 4. So we don't need to label it up in this instance. There are some situations where we will have to label it up, but they won't involve 12 possible outcomes. Now, speaking of 12 possible outcomes, that's important to know, right? So outcomes in the sample space is 12, so that's our denominator.
So did the number 6 come from the die 6 times?
Yes. All right. So 12 possible outcomes. And we just get that by counting up the number of branches. Now you could actually count up from beginning to end and say, okay, I'm starting here, I'm going to H and going to 1, that's one pathway. Then I'm going to from H to 2, to 3, to 4, and so on, and get all the way down to 6. But you could also get it just by counting up your last column, right? Because that should be the end point of every branch. However many there are in that last column should also correspond to the total number of possible outcomes or total number of branches or pathways, right? Now, what I want to do is determine the probability of getting a heads and then rolling a 5, right? So it's not like the either or situation. We don't have to worry about getting a heads and a 5 like on the same coin. It's a matter of getting a heads on the coin and then getting a 5 on the die. All right. So all I'm going to do is highlight the pathway or pathways. Sometimes there's more than one. That's going to get me that outcome. So first I got to get to a heads. Then I got to get to a 5. Once that happens, I know what my pathway or pathways are that lead me to a positive outcome. All right, and all I'd have to do is count up the total number of pathways that I have, and that'll give me my probability. All right. Now, if there's more than one way to do that, then I have to account for that. But in this case, there's only one way to get a heads and then a 5. So I'm following this pathway all the way to the end. That's one outcome out of the 12 available. And so there you have it. All right, so pretty straightforward, simple, not too bad. The only issue is the same issue that we had before when we tackled the reds and aces question is, well, there's only 12 outcomes, so it's not too bad in this case. But what if I had to roll a die 3 times? You got 216 outcomes. I'm not drawing a tree diagram for that. You know, on a test, if I wrote create a tree diagram for tossing a coin and then rolling a die 3 times, your hand should go up asking if that's a typo because it's a typo. All right, either that or I decided instantaneously, like in that moment, that I hated every one of you. Like that's the only way that would have happened, and at which point you would have every right to be like, well, class, we're all in agreement, yes, we're not doing this question? Yes? All in favor? Aye? All opposed? Okay, good. We have decided as a group we shan't be doing this question because there are 532 outcomes. That's going to take the entire exam period. All right? So, and in that case, that would just be a great moment. But I'm not going to force that to happen now. I just kind of played it out in my own mind. So it's kind of like we had that exchange. So it was fun. You all did very well in that moment. But yeah, like it gets out of hand quickly. That's the whole point. Right? So we don't want to have to draw a diagram. However, sometimes drawing a portion of a tree diagram, even for a very complicated situation, can get your brain thinking in the right direction. Because you might not think that you know the rule. But then once you start drawing out the diagram, you're like, all right, I don't have to do the whole diagram in order to know that I'm going to be multiplying here. All right, so now I know I'm using the multiplication rule. Okay, so now I know what to do. All right, so it just kind of gets the memory jogged a little bit, gets you thinking in the right direction, and then sometimes that's all it takes. All right, because it's great if you could jump right to this rule: probability of tossing a heads and rolling a 5 is the same as the probability of getting a heads, which is 1 out of 2, multiplied by the probability of rolling a 5, which is 1 out of 6, which results in 1 out of 12. I mean, you could do that out. That's easy enough. People who struggle in probability, they don't struggle with that part of it. They struggle with the part where they understand that they need to do that, right? They get jammed up going from here to here. not from here to here to here. This part is almost done. Once you get to this step, oh, okay, once I figure out this and that, I'm just multiplying, that's fine. Knowing that these words mean for you to multiply, that when people struggle with probability, that's where the struggles happen. All right. So it's part of it's training and studying, but part of it is trying to diagram out the situation, understand what the scenario is really talking about, and then kind of going from there. All right. So we'll do a couple examples, and I'll gear you towards that.
Professor, if somebody asks you, you need to draw a heads and or a 5, then it would be 2/12, right?
Heads and or a 5, then it would be 2/12, yeah. Because then it allows for tails to be involved. Exactly. Very good. Get rid of this stray Mac. Okay. So, multiplication rule for independent events is what we just talked about. Indirectly, I like to do it that way. Because, giving the formal rule first out of context doesn't really do much. Independent events, statement here, probability of the second event occurring is unimpacted by the fact that the first event has already occurred. Now, if I let off with that, it's like, okay, cool, those are words, nice words, cool, moving on. But in this case, it has, I think, pretty good meaning, because when we were talking about flipping a coin, whether I got a heads or a tails, that was not going to impact whether I got a 1, 2, 3, 4, 5, or 6 when I rolled the die. Didn't matter if I got a heads or tails. I was always going to get 1, 2, 3, 4, 5, or 6 when I rolled the die. Right? But sometimes you run into what are called, they're practically read verbatim when I wrote them. Okay, well, every now and then you start dealing with what are known as dependent events. And actually, every now and then, meaning in math class, but in real life, all the time. It's more frequently that you run into dependent events than you run into independent events, right? Because you actually have to start going out of your way looking for independent events, because anything that's dependent, it would be based off of a conditional, an if-then.
So the first thing you rolled the die, that was an independent event.
Correct. So anything that's condition based is going to be dependent, because if you're dealing with if-then, it's a cause-effect relationship. All right, subject, predicate, however you want to say it. But really, it's one leading to the other. All right, so we need to account for that in probabilities, and sometimes it's intuitive, and sometimes you have to kind of take additional steps. All right, so I mean, something as simple as for me, it's very simple in the morning. Pants or shorts. I mean, it's pants or shorts. Everything else kind of comes into play. It's best available t-shirt. At the high school, I kind of set the bar low. First day that I started there, like 12, actually it's 15 years now. I walked in there with like a ratty polo shirt. Because my first teaching job, I walked in with a shirt and tie and like nice shiny shoes the first day. Set that bar too high. So now any day after that I walked in and I was not wearing a shirt and tie and shiny shoes, they were like, "What are you, slumming today?" So second job started off right. There were like holes in the polo shirt, like ratty jeans. And they're like, and so any day that I come in with anything even remotely pressed, they're like, "Oh, fancy, going on an interview?" So like I got it all figured out. So it's best available t-shirt, and by that it's like coolest, or if I rewatched the movie the previous night and studied it a little bit more. I'm on Star Wars Blackout right now because the upcoming movie, so I don't want to mess with that. So I did a little rewatch on Crimes of Grindelwald last night in the Harry Potter series. That movie, it's just filler, but hopefully the next one will be pretty good. But yeah, so that's this one. Anyway, it's pants or shorts every morning. but it is dependent on a piece of information, and we've gone over this before. It's the weather, all right? I asked Alexa, what's the weather? She said, freaking cold. That's what she said this morning. And so I said pants, all right? So it's a dependent situation. So I got it off, it's a probability question. It's a conditional probability question, right? First, I have to look at the probability that it's going to be cold. Then my probabilities are simple, because depending on whether it's cold, there's a 50-50 chance, right? My chances of wearing shorts or pants in my own mind without looking at the weather, 50-50. Like if I black out curtains, I don't look outside, temperature is stabilized inside the house. If I was oblivious to the outside weather, 50-50 chance. But that probability is changed once I ask Alexa what the weather is. Because now my 0.5 just turned into something else. My 1 in 2 chance just turned into a 1. A probability, a certainty for either pants or shorts based off of what she says for the weather. So I said, Alexa, what's the weather today? She said, freaking cold. And then I said pants, all right? It wasn't a question anymore. Now, she might give me a different probability, she might give me different information, which leads to a different probability, all right? So 75 is really my cutoff temperature-wise. If it's over 75 degrees, I'm definitely wearing shorts if the high temperature is over 75, right? If the high temperature is under 75, depends on how close I go either way, because it still has to get up to 75 degrees. So 75 degrees at the hottest time of the day still means it could be like 50 degrees at the coldest time. Do I want to wear shorts at that period of time of day? I don't know. So you get into some gray area, but it's still not 50-50 at that point. Right? No information, 50-50. Give me some information, now it changed. The probability has moved off of that 50-50 mark. That's what dependent events mean, all right, contextually. The probability has changed from what it was or what it should be to something new based on some information that you have been given, all right? So that's the real life case. So let's not do that right yet, because that's hard. Let's go back to some cards and flesh out some different cases, and then we'll go to the real life cases. All right. So two cards. However you flag your notes, I would flag this, highlighter, whatever. 2 cards. Because for the other questions, it was a single card is drawn. This one is 2 cards are drawn. All right, multiple events. So we're dealing with the multiplication rule. All right. Now, the one thing you got to be mindful of, probability, there's a lot of moving parts. So there's always a bunch of things that you need to be mindful of. But one of the main things you have to be mindful of is that you're not just limited to one rule in every scenario. So sometimes you're going to have to use addition and multiplication, right? So that's not the case in the first one, but in the second one it will be, right? So let's baby steps here. So probability of a king and an ace in that order. Now, this is a key phrase here. In that order is implied. Based off notation. So it's actually an extraneous statement, but since we're just getting our feet wet with this concept, it was worth saying it this time. If I say probability of a king and an ace, even if I don't say in that order, I mean in that order. I mean, we all do. So if you write that, you mean in that order also. The only time I mean in either order is when I say in either order, right? Like in number 2. So in number 1, the words in that order did not need to be there, but in number 2, the words in either order do need to be there in order for the question to mean what I intend it to mean. All right. So probability of getting a king times probability of getting a king, I'm sorry, getting an ace. And I'm going to draw a vertical line, and then I'm going to write a K. All right. This is weird, so I'm going to explain. That vertical line means given that. All right. It's a condition. All right, so that's Alexa. All right. So this reads as, I want the probability of getting a king multiplied by the probability of getting an ace, given that, so just that vertical line means given that, I already got a king. All right. So the second card being selected is assuming that the first card selected was a success. All right. So this is telling us that we're assuming that this happened, that the king was selected from the deck, and also not replaced in the deck. All right. So you had 52 cards. You shuffle them all up. You deal out just one card. You deal out a card. You're looking for the probability that it's going to be a king. All right. That's easy enough. You go back to the sample space, 4 out of 52. All right, there's
4 over 51.
times 4 over 51. All right, because once I remove a king from the deck, right, I had any 4 possibilities that could have come out of the deck. I got one of them. I got the king of spades, the king of hearts. It doesn't matter which one it was. You got a king. All right, it happened. Throw it away. Now you only have 51 cards left over. All right, 51 cards. But all the aces are still there. So you still have the 4 aces that remain. All right. So again, with the probabilities, I like to think about the classroom. I go back to that. You have 52 cards milling around the room. You got the kings, you got the queens, you got the aces, and all that. All right. So in this context, I'm saying, all right, all the kings, do me a favor, come up to the front of the room. I need to talk to you. So the kings come up here, and I say, okay, I just need one of you. All right, do me a favor. The rest of you, get out of here. I need you to go down to my office and grab my tablet for me. All right, so that king leaves the classroom. All right, so then I need another volunteer. So I say, okay, well, I need an ace to help me out. All right. So now out of the 51 people that are left in the room, I say, okay, all the aces come to the front of the room. There's only 4 of them that are going to come to the front of the room. All right. So in this context, it's who's going to come to the front, who's going to volunteer to participate. All right. I like that analogy, the physical in the room analogy, because it doesn't just talk about cards. All right. And when you expand to the real world, a lot of the times, when you conduct your own studies, it's going to be related to people. So why not start to personify some of these concepts? Why not make the sides of the dice people that can raise their hands, and do it that way? All right, it gives you a visual, and it makes it a little bit more accessible. All right, now it's just a matter of multiplying. So if you're in doubt on how to perform an operation, just do it in your calculator, because I don't want you getting questions wrong because of the computation parts of it. All right. I don't want you getting questions wrong, period. But the number of people who have forgotten over the years that the product of two fractions is the top times the top and the bottom times the bottom. It's not a common denominator. It has blown my mind, right? So it's, and not because it's like, oh, how could they not know this? Math, kids these days, you know, it's not like that. It's more like, you have a friggin' calculator. Type it in. If you're not sure, just type it in, crying out loud.
Just trying to quickly understand. So the two cards is the king one and the face,
Correct.
right? So there's 4 kings on 52 cards and 4 aces in that 52 cards as well.
Right.
But since you pulled 1 king out of 52, that's what the 51 is.
Exactly. All right. So, like I said, when in doubt, put it in your calculator. All right. It may give you a simplified form of this. Cool. We'll take the simplified form. All right. You do it this way. Now, the 52 times 51, you could tell how many times I've worked with these numbers. It's just, I know 52 times 51 is 2652. I know 52 times 52 is 2704 because I've done these problems like 1,000 times. And I don't think, honestly, I don't think that's an exaggeration. It's pretty crazy after all these years when you deal with the same concepts over and over again, just how many times you end up multiplying the same numbers. You know? So if that didn't pop into your mind as something obvious, then don't worry about that. But yeah, the calculator is very helpful. Now, if I said 50 times 50, yeah, you should probably be able to figure that out. But these two. King and an ace in either order. All right, so that means that you can go both ways. So it doesn't say the word or in there, but it says or's partner, which is either. Usually you don't get one without the other. I typically don't think, I mean, you can see it sometimes, you see it right here. I typically don't think of the word either without the word or somewhere close after. So what we're looking at here is just a kind of intermediate step. I'm going to say king and ace or ace and king. All right, king and an ace or an ace and a king. You got good news and ever so slightly less than good news. But there's no bad news. All right, the good news is we've already figured out the first part. We did that in number 1. All right, I'm just going to write it a little quicker, but I'm essentially going to write the same stuff. Probability of a king times the probability of getting an ace given that you already had a king. All right, which ended up being 16 over 2652. Now, the or means addition. All right, we learned that a couple pages ago. Or maybe last page, I don't know. But the addition rule is the rule of or. Right? Anytime you see the word or in a problem, it's telling you to add probabilities. All right. So the question would be, add what? Now, I look at or as kind of like a reset button. It's basically saying start the problem over, put all the cards back in the deck, and recompute. All right. So this is saying, okay, new scenario. Now I want the probability of getting an ace, which we know is 4 out of 52. Because again, we're starting over. So probability of getting anything in a deck, whether it's a 2 or a 10 or a jack, they're all going to be 4 out of 52 because all the cards are available. All right. Times the probability of getting a king given that the first card selected was an ace? All right. So again, going back to my analogy, all the cards are milling around in the room. I called all the aces to the front of the room. I sent one of the aces out of the room to get me a cup of coffee. There are 51 cards left in the room. I just want to know how many of them are going to be aces. So I call, how many of them are going to be kings. And I say, okay, all the kings come to the front of the room. There's still 4 of those. All right, so what we get from this, if you compare it to number 1, it's the same computation, same stuff. All right, we got 4 out of 52 times 4 out of 51. All right, same exact calculation. Different order, didn't matter, same result. All right, so ultimately, all we had to do was take the answer for number 1 and double it, and we would get number 2. So we're looking at 32 as a final answer over 2652. So we doubled the order in which we can get the possible outcomes, so we doubled our chances of success. And you think of that, I mean, hopefully that would make some sense. If you're playing a lottery, for example, I'll keep it as a very simple lottery.
Another question, because I got a different number. I got 56 over 2652, but it's because, like first you can get either a king or an ace, right? So the probabilities are 8 over 52, because you can get, like any of those. And then it will be, for me, times 7 over 51, because you have removed 1 card, and then, like you're not...
The problem with that...
You can get either, like one of those 2 groups lost 1, so I multiplied those, and I got 56 over 2652, and I didn't do that.
The problem with that is you're allowing for king and king, and also ace and ace. Because when you lump them all together, it's basically me saying, okay, I want all kings or aces to come to the front of the room. So now if I'm selecting 2 out of that group, it's possible that I could get 2 consecutive kings, or I could get 2 consecutive aces. This is just, it's calling for a king then an ace, or an ace then a king, but never a case where it's king and king or ace and ace. All right, so if you were to list out all your possibilities, what you're looking at you're looking at king, king, so 1, 2, 3, 4. 4 of the kings, 4 of the aces, all in one lump sum here. And so if
no,
the...
I got it, Professor. And then, like if you replace 8 over 52 times 4 over 51, then you get 32.
Right. Yeah, so then that, okay, good. All right. What is this? Lost it. It was something. Probably not that important, so we can move on. All right, so the next 2 questions are a little bit, I don't want to say trickier. They have some trick to them, some thinking to them, but I'd rather you do the thinking first before I spoil it all for you. So I'll put some stars on these bad boys, and we'll tackle these 2 next class, so you have an opportunity to practice with those also. Window shift.